Okay, everyone, welcome back. Exponential functions. So I asked you to go home and graph some exponential functions. Anybody have any problems with that? Anybody have any issues? You should have some of those y values might have got pretty big. Yeah, that's okay. So this up here is kind of a summary of what we did last time, but written out a little bit more mathematically, as opposed to me just like tearing up pieces of paper and talking to you about it. So when we have exponential functions, all ready? Come to class, then you'll know what's going on. All right, exponential functions. When we have them, these numbers, the number down here, the base is what we call it, right? I gave you problems to do where I gave you different bases, right? What were the bases I gave you at home? No, the base, the thing being raised to the x. I asked you to do 3 to the x, half to the x. What else? 2.5 to the x, 2.718 to the x, right? That's what I asked you to do. Those 4 functions, and make a table and plug everything in. The number down here, 3, 1/2, 2.5, 2.718, that is called the base of the exponential function. And I didn't tell you last time, but there are some restrictions on that base. First of all, the base you use has to be a positive number. You are not allowed to plug negative numbers in here as the base. If you do, it's no longer called an exponential function. It's something different, and we don't mess with that in here at all. Also, you can never let your base be 1. And the reason why is because 1 raised to any power is 1. So when you graph it, what it would be is a flat line. It would just always be 1, all right? It would just be flat the whole time. So we throw that out also. The only things that are interesting are when a is positive and not 1. Okay? Now, when you did your graphs, you should have had, let's see, 3 of them should have looked like this, and 1 of them should have looked like this. So what I'm saying here in this little note is that when you graph an exponential function, your graph has to look like one of these. But there is something that will determine which one it is. So how many of you got 3 of these? Okay? And can you tell what kind of dictates that you got this instead of this? Well, okay. Did anyone get this when they graphed? Yes, you should have got this. Okay, so which one was this one? The half, right? Notice that the base of this one being a half, and this one being 2.5, 2.718, and 3. These 3, the top one, the bottom 2, should have all looked like this. And the 1/2 should have looked like this. So what is it that you think is going to determine which of those it is? It's the A, right? If it's bigger than 1, right? Because it can't be 1, right? So if it's bigger than 1, it's going to look like this. And if the A is less than 1, it's going to look like this. So I'm going to put that here. This is what the graph looks like if your base is bigger than 1. And this is what the graph will look like if your base is less than 1. So 1/2 is less than 1, right? If I were to ask you to graph 1/4 raised to the x, then it would look like this one. If I ask you to graph 10 raised to the x, it would look like this one. And they also all have a 1 point in common. They should all have the point 0, 1. So if you look back at all your graphs, every single one of them, when you plugged in 0, it should have spit out 1. Got it? All right, so this graph right here, we refer to this one as exponential growth. Exponential growth. And this one right here we refer to as exponential decay. With all of the political stuff going on right now, I was listening to several news channels on the night of the election, and I counted. I heard exponential 3 times. 3 times. I was just sitting there going, yep, there they go using that word again. Trying to say that something's growing fast, right? That's what they were trying to say. So exponential growth, something is growing very fast. Exponential decay is kind of the opposite. It's going away very fast. With me? All right, now there was one particular one that I asked you to do, this one. And you might be like, well, where did he get the 2.718 from? Is that just, he just made up that number just for fun? Well, it turns out that that number is a very special number. And that's what I want to start today with. A very special exponential function. All right, a special exponential function. All right, now before I tell you about this special exponential function, I want to ask you about numbers for a second. Do y'all know what the number pi is? Like, does anyone know what that number is? Approximately, what? 3.14, yeah, we use this little squiggly equals and we say 3.14. Now, do you all know that pi is called an irrational number? Have you all heard that before? What does that mean? That it's irrational. You just can't talk to it. It's like real stubborn. You know, you say something to it, it's irrational. What does it mean? Obviously, it doesn't mean irrational like the same sense that an irrational person, right? It actually comes from this word ratio. Okay, when you think ratio, do you think fraction? Okay, this number pi is not a fraction. In other words, there's no fraction I could come up with that would give me that decimal. I'll give you an example. If I write the number 3/4, we all know that's a fraction, right? And if I get that as a decimal on my calculator, I'm going to get 0.75. If I take 1/3, I'm going to get a number like 0.333, and it'll keep going forever. This will be a repeating decimal. Just 0.3 forever, right? With me? Is there a fraction? Can I create a fraction, plug some numbers in here, that would give me pi? And the answer is no. It's impossible to create the number pi from a fraction. So it is irrational, not a ratio. Does that make sense? So what makes pi unique is not only is it a decimal that keeps going forever, like this one. See, this one goes forever, right? This one goes forever, but it never has a pattern. It never repeats itself. So like 0.333 just goes forever, but it's a repetition of the same number over and over and over, which is, you can predict what's going to happen next. Where pi keeps changing, there's no pattern, you can't predict the next number, and so it's kind of a weird number. There are actually a lot of numbers that are like this. So pi is a very special number in our number system, and we use it for finding areas of circles and things like that, circumferences and blah, blah, blah. But there's another very important number in our math system that's so special that, again, we represent it with a letter. See, this is a number, right? But we represent it with a letter. This is pi. This is a Greek letter for P. All right, pi. So there's another number, a very special one, that we use a letter for, and it is the number E. And it is approximately 2.718, which is why I gave this to you. Okay, I wanted you to do that graph first, and then we come talk about E. So E is also irrational. You cannot predict the next numbers, and it keeps going forever and ever. But what makes it so special is very difficult for me to explain to you in this class. You actually have to get into Calculus 1 before I can actually make you believe that that's a really good number. All right? I hate to say that, but that's the way it is. All I can tell you is this. When you graph it, well, maybe you can tell me this. If I ask you right now to graph the function f of x equals e to the x, That's the same as me sending you home with this problem, isn't it? And when you graph that, you should have gotten this particular, just roughly speaking, that's what it should have looked like, roughly, right? You got exponential growth. These three were all growth. Let me take this one out of here. Those three were all growth, right? And if you were to graph all three on the same graph, put them all on top of each other, they would be different, wouldn't they? They'd all be growth, but they'd be different. This particular function grows in a certain way, just the way that it goes up, how fast it goes up, the rate at which it's growing. It just so happens that this is the only function that grows a certain way that in calculus we need. And all right, so again, it's kind of like I can't trying to think of an analogy here. I'm terrible with analogies. It's kind of like me trying to teach you how to paint a house if you've never seen like a house or you've never worked with paint before. You know, it's like it's hard for me to explain the value of this function to you without you actually getting into the calculus perspective of how we look at these functions. So you're just going to have to take it on faith that in a class like this in college algebra, what we're trying to do is just introduce you to this function. Trying to sell you on the idea that it's important later. And what also makes it special is the fact that it's the only function that behaves this certain way in calculus that we need it to behave. So there's no other function out there that exists that does what this one does. So we sit here as humans and we go, okay, well, why is this one so special? Like, what makes this number so special? We can't really explain it. It just kind of works. So we have a name for this function. It is called the natural exponential function. And the word natural, okay, so I'm referring to this function right here. The word natural is kind of like, you know, when you go out and you look outside and there's a flower and there it is, and that's just the way it is, right? That's just the way nature has made that flower. This function, we can't explain why this is the number that does it. It just kind of naturally happens. This is the one, all right? All right, now, you're going to see this E thing come up in just a second when we start looking at these financial problems. But I want to make sure everyone can find that E on their calculator, all right, before we move on. So please look on your calculators. I've asked you to bring them from now on, right? We're going to need them quite a bit. So let's see, where is that key on your calculator? Let's see. Yeah, okay, so you should have a button on the left-hand side, if here's your calculator. Now, of course, some of you don't have the required calculator, but there should be a button here that has this on it. What is that? It looks like in, right? But it's actually a lowercase l followed by a lowercase n. And it stands for the natural log, which we haven't even talked about yet. All right? This is log natural, French. You know how they do things backwards? Logarithm naturel is what that stands for. So above that, like in green, is it in green? There's a little e to the x key, or a little e to the x above that. And since it's a green, you have to hit that green, does it say shift up there? Second, okay, so you have to hit that second key first. So what I'd like for you to try here is let's try and do e to the first power. All right, to do that on your calculator, you should do, double check how we're gonna do it. So you hit the E first? Okay. So hit the second key. Man, someone smells good. It smells like a fruit basket in here or something. Second key, then hit that LN key. And then on your screen, it should just be E. And is it like blank up here, like blinking or something? Yeah? And you're now going to fill that in. So when you fill that in, put a 1 there, and then hit enter. So you hit 1 next, enter. Was there a parenthesis there? Yeah, it was. There was a parenthesis? Yeah? Okay, then you would close the parenthesis. Okay. Yes. And what do you get? What does your calculator say? Does everyone get about 2.718? All right, so that's what e is. E to the first power is about 2.718. And then you could continue from that and you could do e squared and e cubed, right? You could do different numbers. Let's try one more. How about try e to the negative 2? Tell me what you get. Error? Let me see how, yeah, this is why we're doing this. I want to make sure you know how to type this in. Negative 2, there you go. Yep, not the minus, yeah. So you should get approximately what? 0.135. Okay? The reason I'm doing this is because everyone needs to be able to get this on their calculators. If you can't, that's not my problem. I'm here to help you now, but on the test, if you can't get this, that's your problem. Understand? So you got to make sure you know how to type these in. Anyone have a question on their calculator how to do this? We're all good? Okay? All right. We will play with this. We will play with this in a little bit. All right? We're gonna move on. We have this very special function called the natural exponential function. Let's switch gears here and let's go to some personal finance, all right? Okay. In particular, we are going to look at something called simple interest. All right, simple interest. So just in case you don't know how it works, let me show you how this works. And this, I'm kind of making this very simple. I don't know if there's a lot of more details that we could talk about. Here's a bank, okay? Here's a bank. You like the bank? Yeah, there's a bank. Now, here you have people over here. Let's say you have a person here, and they have a credit card. The credit card is issued by the bank, right? So they go here and they issue them the credit card. So they're borrowing money, right? I'm not going to ask you if you have a credit card, but if you have a credit card, what you're doing is you're saying, hey, I'd like to borrow money from the bank so I could go buy my new whatever. And then what I'll do is I'll pay the bank back, but I'll pay it back over time. So I'll make monthly payments or whatever it is, right? But when you do that, you're charged interest, right? So let's say you borrow $100, you may at the end of the day wind up paying back $140, right? So when you have a credit card, what type of interest rates do they use? Are we talking like, 5%? What do most credit cards have as interest rates? Do y'all know? If you have a credit card, you need to know, all right? It's usually above 18%, closer to like 20, all right? So you're talking, let's go with the low number here, 18%. That's not 18%, that's 18 degrees. Okay, 18%. All right, so the bank is looking at it this way. Look, I'm going to loan this person money, right? They're going to pay me back. And when it's done, I'm going to make money, right? Because they're going to pay me back more than they borrowed. The only drawback is I have to wait, right? I have to wait over time for that money to come back in. Make sense? All right. Then you got the person over here who says, you know what? I'm working. I'm going to put my money into the bank. All right. So I should put an arrow here. Money came out of the bank. This money is the person that's putting money in. So they are investing money into the bank, right? So you get your paycheck or whatever. You go buy all your groceries and gas and everything. You got a little bit left over and you put it in your bank. And the bank says, you know what? For giving us your money and allowing us to hold it, we're going to pay you for your money. We're going to give you money for your money. All right? And the rates are usually, what do you think the rate is on the money they give you? Crap. It's like 1%. Okay? 1 to 2%. All right? If you're lucky, 3, but 3 doesn't happen anymore. I'm just going to say 1%. So this person sitting over here is like, look, I'm going to put my money in the bank. At least it'll be safe there. And I'm making a little bit of money off of it, right? Now, do you see how the bank makes money? They're actually, the money that they're loaning this person is not their money, it's their money. And so they're just exchanging money back and forth. That's all they're doing, all right? That's the way a bank works. how your interest is computed, right? How you can determine how much you're going to owe, like if you take a credit card out and you pay it over a certain amount of time, like how to determine how much you're going to wind up paying at the end, we use a simple interest formula for. And there are two of them that are widely used, and I'm going to show them both to you. And then we're going to work with them a little bit. All right? Understand? All right, so here we go. There are two major formulas for computing simple interest. The first one, and this is this is the one that we use when we have compounded interest. And I will explain what I mean by that in a second. Just write this down. Compounded interest. The formula is A equals P parentheses 1 plus R divided by N raised to the N times T. That's the formula. And I'll explain it all, just write it down for now. The second formula, hold on. I don't know why I put compounded interest there. I meant to say, put periodic. Periodic compounded. I'll explain it, don't worry about the naming of it right now. This one over here is called continuous compounding. Again, don't get caught up on the wording of things, all right? So there's one formula, here's the other formula. The other formula is A equals P times, so far it's the same formula, right? A equals P. This is a times right here, all right? Then there's all this junk in here, right? This one over here is E, that number, right? 2.718 raised to the R times T. I call this the shampoo formula. For those of you who know, but I know some of you use PERT Plus shampoo. No? Just me? I'm the only one. Okay. Have you heard of PERT? PERT shampoo? No? All right. It exists. All right, so never mind. This is not the shampoo formula. This is just a formula then. All right, PERT, P-E to the RT. Which one of those formulas looks easier to work with?
The first one.
You like the first one? Yeah? You like the second one? Okay, well we'll see. We're gonna use them both, and we're gonna see which one's easier. But let's discuss what all these letters are, because it's a little overwhelming when you look at all these letters, right? All right, so the first letter let's start with is A. So I'm gonna write down up here what these letters represent. Well, let me go, not A, let's start with P. P, all right, is the amount of money initially borrowed or saved, you could use the word invested. All right. Now the technical name for P is principal. Okay, the principal is the initial amount. So when you go and you charge on that credit card the first time, that charge, that $500 LCD TV you just bought, that's your principal. Okay, the initial amount of money that you borrowed or was the other guy who puts the money in the bank, right? That's how much he saved or invested. All right, so that's what P is here, and that's what P is here. Got it? All right, the next letter in this thing is R, which is the interest rate. And the interest rate is determined by the bank. The bank is going to say how much they're going to charge you for that credit card, or it's, how much they're going to give you for you giving them the money. 18% if you're borrowing and 1% if you're giving them money. It's important in the formula. In the formula, you must convert to a decimal. So remember, if you have something like 18%, what is that as a decimal? Do y'all know how to convert percentages to decimals? You look at the decimal point, which is right here, and you move it to the left 2 places, so this would be 0.18. So in a problem that has an interest rate of 18%, in the formula, you would not put 18 here, you would put 0.18. Got it? Don't make that mistake, because everything will be wrong if you forget to do that. All right? Okay, how about t? T is time. And it's important in these finance models that we're using here. Time is measured in years. Now that's important, all right? To say that time is in years. Because what if you say that you're going to borrow money for 6 months? Then t is not going to be 6, right? T is going to be like 0.5, half, something like that. So you need to pay attention to that when you're doing the problem. All right? What's left? No, E, remember E is 2.718. So that's never going to change. That's good news for us, that that's not something that's going to change. A is there. There's also another one. N. Okay, so let's see. Let's do A first, because N is the one that's the most confusing. Okay, A is the amount owed or saved at the end of T years. So the left side of this equation is like the output. It's going to tell you, hey, if you borrow a certain amount of money at a certain interest rate for a certain amount of time, this formula will compute how much at the end you're going to wind up paying back, how much you're going to owe total. That makes sense to you? That's when I was saying, like, if you borrow $100, but at the end you might wind up having to pay back $120 because you borrowed that money, right? There was an interest rate to it. So the A is the amount that you're going to wind up at the end of the day having to pay back. All right, and that just leaves N. N is the only thing left in here, right? And do y'all notice that N is in this formula, but N is not in this formula? N is here, and N is not here. This N is confusing, and it's somewhat hard to explain. I will do my best. Let's see if you can follow this. Let's say you borrow $100 for 1 year at 10% interest rate. How much are you going to pay back at the end of the year? $110. So it was the 100 you borrowed, plus you have to pay back 10% of that, right? And 10% of 100 would be $10, so you add that together, you get 110. We all good with that? In that case, N would have been 1. Okay? Now, let me give you a different scenario. You borrow $100, and it's still 10%. Yeah? But you're going to make 2 payments. One at 6 months, and one at the end of the year. Make sense? So what they're going to do is on your first payment, let's try and visualize this. On your first payment, here's the $100 you borrowed, right? When you make your first payment, they're going to take half of what you owe, all right? Half of what you owe, which is 50, and then do not 10% of that, but half of 10% of that. And so like halfway through the year, you have your interest computed, and then at the end of the year, you have your interest computed again. So in other words, your interest is computed twice, but it's on half of the money at half of the percentage. Yes?
Is it like annually and then like
Yep, that would have been semi-annually, what I just said right there, right? Twice a year.
Because I took statistics last year.
Yep.
That they would use annually and
Yep, I'm going to use those too. I'm just trying to get you to think about it first, okay? So N, actually, in the formula, N is how many times how many times they're going to compound the interest per year. So if they only compound the interest one time, then that would be annually, that would be 1. If they compound the interest twice a year, then it's semi-annually, and N would be 2. What if they compound the interest quarterly? That's 4 times a year, so N would be 4. What if they compound the interest monthly? N would be 12. Understand? Now, sitting there as a student, you might think, okay, look, the bigger the 12 is, the worse off it is for me, right? You might be thinking, look, the more times they compound the interest, I'm gonna owe them more money, right? Like, please, let's let N be small. But it actually turns out that it doesn't have as much of an effect as you think, because every time they make the N bigger, they're actually cutting your money up into a smaller piece. And the impact that it has is negligible. So as N gets bigger, so I started out at annually, right, once a year, then I went to 2, then I went to 4, then we went to 12. Another thing they could do is compound your interest daily, which would be that N is 365 if we use 365. That's even bigger, right? And you would think, well, it's going to make this huge. It's actually not going to make it huge. And then they have something called compounding continuously, which means that every instant in time, like all the time, they're compounding your interest. Like as I'm speaking, they are compounding interest the whole time I'm speaking. Now that might sound, again, like terrible news to you, right? But that's actually this formula. If you let this N become infinity, and this N become infinity, this big mess turns into this nice formula. And it works out that the difference between these two answers are going to be pennies. All right? So the N in the problem is officially the number of times the money is compounded per year. So remember, if you need to make a note here, once a year is annual, twice a year, semi-annual, 4 times quarterly, 12 times monthly, 365 would be daily, and then we won't go past that. All right? Any questions? All right, we're going to do an example. We're going to figure out how much money you would owe at the end of a certain amount of time if you took a credit card. All right, so let's try this. So you're going to borrow money. Now, this formula is not going to be perfect because we're going to assume you're not going to make any payments. All right? We're just going to say, how much would you owe at the end? All right? So example is this. You borrow, how much do you want to borrow? 1,000?
Yeah.
No, how much?
$1,500.
$1,500. Okay, you borrow $1,500 at what percentage rate? You want to do something pretty realistic on a credit card? Let's do 18%. I have a credit card. Actually, I don't use credit cards, okay? I'm fortunately at a point in my life where I do use credit cards, but I only use them when they have the option of no interest for a certain amount of time. So like I got a credit card last year that is no interest for 26 months. So I can make a purchase and pay no interest on that for 26 months, which means I can pay it back to them at no interest. So it's like someone just walking up to me and handing me whatever, you know, and they're handing it to me and they're saying, hey, just pay it back whenever you want. You have 26 months and we're not even going to charge you for that. I'm like, great, okay. I'd rather have that money, you know, in my pocket than. But here's the thing: you have to qualify for a card like that. You have to have credit. You have to have good credit. Now, if you're on the end where you're just developing your credit, that same card, they'll probably give it to you. All right. But the thing is, most people aren't disciplined enough to make the payments, and so they hit that 26 months. And guess what they do at that 26 months? They say, all that interest you didn't pay, now you get to pay it. 26 months worth of interest. That's why if you go and you see all these promotions like no interest, no payments for a year, they are banking on the fact that you're not a responsible, person with your money. So you're for 1 year, you're like, I'm not making these payments, and all of a sudden, boom, they all come at one time, all the interest is there, and you're screwed. Make sense? So you have to be careful with credit cards because that's how they get you. And the credit card I have that has no interest right now, if I let it go past the time, it's 26%. So they have enough people that mess it up that they can afford to let me, be okay. All right, so you're going to borrow was there a question? All right. You're going to borrow $1,500 so you can go buy, what, a big screen TV? Okay, good. You borrow $1,500 at 18%, and how long do you want to have this for? Like, your goal is to try and pay it off within the year, 2 years? Let's use 2 years just so we have a number other than 1, okay? You borrow that much money at 18% for 2 years. We have to break this problem down into 2 pieces now because we have 2 formulas, right? So I'm going to give you 2 different scenarios. First of all, how much would you owe if interest is compounded? What do y'all want to do? Annually, semi-annually, quarterly, monthly, daily? Quarterly. You want to do quarterly? Everyone sound good? That sound good? If interest is compounded quarterly. That's the first thing. Second thing, same question. How much would you owe if interest is compounded continuously? So basically the first problem is telling me I'm going to use that first formula, and the second one is the second formula, right? So let's identify the pieces to the puzzle here so we can fill in our formulas. What information are we given? You borrow $1,500. What's the $1,500? That's your P. Okay? P is $1,500. That's how much you borrow, right? That's your initial borrowing. All right, what about the 18%? What is that? That's your R, but we've got to convert it, right? So R for us will be, I'll put 0.18. You don't have to put the 0 there. I'm just putting it so you don't forget the decimal. All right. What about the 2 years? That's time, that's T, right? And remember, T is measured in years, so I'm just going to put 2, right? So 2 years. Anything else I have? I'm going to be looking for A. That's what I'm going to look for. The compounded quarterly, right? That would be, N is what? 4, right? But that's only going to work for this formula, right? For this formula, I don't need N, do I? Okay, so I'm going to actually do these 2 problems now. So the first one, I'm going to state here for this one, N is 4, right? That doesn't apply to this second problem. I don't need it. So let's say N is 4. Now let me write down the formula. The formula I'm using is A equals P times 1 plus R divided by N raised to the N times T. And now I'm just going to use that formula and start filling in the blanks. So the amount that I have will be the $1,500 plus, 1 plus times 1 plus 0.18 divided by what? 4, all raised to the 4 times 2. All right, now we need to be able to use our calculators to do this. So what are your order of operations? Parentheses first, right? So we got to do what's in here. And when we look in here, we have addition and division. So we're going to do division first. So on our calculator, do 0.18, divide that by 4, and you get 0.045. I'm going to go very slow here, since this is our first one. 1 plus 0.045 raised to the, can I just go ahead and multiply that? 4 times 2 is 8. All right. All right, now add those together. 1 plus 0.045 would be, let's see, 1,500 out here. And then isn't that just 1.045 raised to the 8th? Now, order of operations. What are you going to do first? 1.045 to the 8th power. So make sure you can do that on your calculator. Hey. Psst. Psst. Hey. Do you need to walk around? You okay? All right. All right. You know how to do this on your calculator? You're going to be okay with that? All right. 1.045 to the 8th. Okay, when you do that, you get this real long decimal, don't you? 1.422, right? Use every single number that you have there. Because the more accurate this is, or the more decimals you use, the more accurate your answer is going to be. So let's go 1500, and then I'm going to have this right here is 1.422100613. Does anyone's calculator go further than that? Did anyone not go that far? Okay. So we're good? Now, this times this. So 1,500 times 1.422100613 is 2133.15, and I'm going to stop at 15 because this is money, right? So we're not going to have anything past cents.
Unless you're paying for gas.
Yeah, that's right. Yep. Good enough. That's close enough. All right? So that means how much interest are you going to wind up paying? How much did you borrow? 1,500. How much did you pay back? How much are you going to have to pay back? 2,133.15. So the difference between what you borrowed and what you're going to pay back is $633.15. Yeah, so if you look at that as a percentage of what you borrowed, if you take this and subtract 1,500, 633, divide that by what you originally borrowed, 1,500. Ooh. What do you get? What do you get? 0.42. That means really, you paid actually 42% more than what you borrowed. You not only paid back what you borrowed, you paid back 42% more than what you borrowed. That's crazy. So this 18%, even though it looks like, well, it's just 18%, it's not, because of the fact that you carried it over 2 years. It's more than that. So that's why you do not want to ever do the minimum payment on your credit card. Minimum payments, it'll just let that thing just keep going up and up and up. And that's why, if you can, avoid credit cards completely, because you're just paying someone else to borrow their money. That's the problem we have in the United States. I should probably shut up right now. It's true, though. It's true. That's why we're in such a tough spot, is that most people are living paycheck to paycheck, and they're buying their groceries with their credit cards, they're buying their gas with their credit cards. And what happens is that if you don't really have that money, if you keep borrowing that money, right? You're borrowing it from a bank, and where's the bank, getting their money? Well, if there aren't, when I drew the picture and there were like people putting money in and people taking money out, the people putting money in, that's different countries. That's like China. Different countries are putting money in. They're investing in us because we are, what do you call that? Materialistic. We just love to have stuff, right? So they say, sure, keep borrowing our money. And then you'll pay it all back, and you'll pay these ridiculous interest rates back to us. And then what happens? People don't pay back, right? And then things get bad. All right, so stay away from credit cards. Better to eat top ramen for several years than to borrow $10,000 that you're never going to be able to pay back. All right, same problem, right? Same problem. Part 2. Now we are using the other formula because interest is compounded continuously. So you're sitting there going, oh my gosh, they're going to compound this interest all the time, at every instant. Even when I'm sleeping, they're compounding my interest, right? All the time. And you're like, oh my gosh, I'm going to owe back like so much money. Let's see what happens. Well, this will be equal to P, which is 1,500. Then E, now R times T is 0.18 times 2, isn't it? I would like for you to do the 0.18 times 2 first. And you get 0.36. So now this is 1,500 e to the 0.36. Now this is multiplication. So I want you on your calculator, which y'all just did this a second ago, right? You did e squared, or you did e to the 1, you did e to the negative 2. Now do e to the 0.36 on your calculator. And tell me what you get. Okay, 1.433329415, something like that? So 1500 times 1.433329415. And I said just go, when you do this, go as many decimals as your calculator goes. Now multiply those. And we're going to round it to the nearest cent. So what was this? 2149.99. What was the other answer? 2133? This actually made a little bit of a difference, didn't it? About 16 bucks or so, $16 difference. I know, I said it would be pennies, but that's a pretty high interest rate. And that's, 43%. This is 43%? Yeah. Yeah, if you're borrowing $1,500 and having to pay back $2,100, I don't think you can complain about $13. That's your fault for getting yourself in that situation. All right, so this formula, though, is kind of the worst case scenario. This is the, there's no other way they could compound it, all right? You know how I said it was like quarterly or daily, or this is worst case scenario. This is them compounding it all the time. But it also works in your favor. If you're the one putting the money in, they use the same formula. They compound it continuously, so you're going to get more money if you put it in. The problem is they keep their interest rates real low. All right, good? Yeah. All right. Let's do a little bit more of a cheery problem. Let's do a lotto winner, okay? Someone who wins the lottery. Let's see how good life is. Now, in your mind right now, realistically, because you're in college, you probably have some idea that at some point in your life you want to have a job, right? That's going to maintain you for the rest of your life, right? A career in something. And in your mind, you probably have like a number, hopefully. Everyone has some sort of number as to what they would be happy or comfortable with as far as living. Like maybe in your mind right now, if I could just make $50,000 a year, I'd be happy. Or if I could make $100,000 a year, I'd be happy. Or if I could make whatever it is in your mind, you have that number, right? If you don't, you should probably start looking into that, all right? So you got your number. Now you win the lotto. Okay. So here's our example. You win. How much do you want to win in this lotto? You want to do something like $1 million? You want to go?
Like 24 million.
You want to be the Mega Millions? Okay, you want to be Mega Millions? So let's do after taxes because right, they're going to take half your money. All right. So let's just say that you win. Y'all realize that's why they take half your money? Why does the government get to keep half your money? All lottos is another way to gain tax money from you, right? That's all it is. It's a tax. Well, it's a tax. That's all it is, right? They say, hey, we'll play this game with you. You pick these numbers, and someone's going to eventually win, and we're going to take all the money that people put in, and we're going to give it to you, but we're going to keep half. So we're going to use that money to go build roads and maintain our schools and have all these different programs. So it's a tax. That's all it is, right? Why is it the Texas Lotto? Why isn't it like Valero Lotto? You know what I'm saying? It's the state that's saying, hey, look, we're going to legalize this gambling almost, right? Just collect taxes on it. So it's their cut. The state wins too. Every time someone wins, the state wins. Okay. So remember we were talking about, could you win the lotto every day of your life? The state does, right? The state wins every single time. All right, you win. Okay, you said 25 million. Let's go with 24 million, and let's say the state takes their half. I'm going to go with 12 million. All right, 12 million. Woohoo! All right, so what do? That's it? Drop out of school. You go, you buy a boat, you just start cruising Miami's coast. What are you doing, you know? What are you doing? You're buying a house, okay? All right, well, let's just see if you were... Let's say that for the first year, let's just say for the first year you had this, you had some stuff you did in your past that you regret, but you're going to have to go serve some time. All right? For 1 year, you're going to have to do this sentence, and once you're done in that year, you can come out, boom, you got your 12 million, you're ready to roll, right? So you decide that while you're in jail for a year, you're going to put this money into the bank, right? And let it work for you. Now, I would never advise anyone to put $12 million into a single bank. You would have to split the money up into several different banks, and then you'd probably make other investments if you were smart with it. But let's be somewhat aggressive in saying that you're going to put it into some sort of investment. And we'll act like it's just one bank. And let's say we're going to get a return of 3%, which is pretty high if it's just into like a checking account. But let's go with 3%. You win $1,200. You invest it at a rate of 3%. And you know what? Let me make your prison sentence a little longer for bad behavior, okay? You invest at 3% for 2 years. Look, if you don't want to look at it as in you're in prison, just look at it as for the first 2 years, your mom or dad tell you that you can't spend that money or we're going to disown you, okay? They know you better than you know you. So they're going to tell you 2 years, you're going to finish school, and then after that, you can mess with your money. However you want to look at it, we're not going to touch it for 2 years. All right? Yeah, let's say you're ready to peel the million off, okay? Yeah, you didn't tell them about that extra million. All right, there we go. All right, so let's do the same questions. Let's do, let's say that you have it in this investment, it's compounded monthly. And I want to know after 2 years how much money you're going to have, right? I'm not going to rewrite the question. You understand what I'm asking though? Okay. Then the other question is, what if it's compounded continuously? All right, so for the first problem, what is it that I need to know? Like, what is it that I still need to figure out for the first problem? Like I have P, right? P is 12 million. R is this rate converted to a decimal. Time is 2 years. But to say compounded monthly means
12.
N is 12, right? So I'm going to say N is 12. And then I'm going to use this formula. A equals P times 1 plus R over N to the NT. And that means A equals 12 million. 1 plus, what's my rate? Converted. 0.03 divided by 12 for monthly, and then 12 times 2. Understand where all the numbers come from? Do 0.03 divided by 12. and you get 0.0025. Add 1 to it. So you should be here, 12 million. You should have 1.0025, and then you're going to raise it to what power? 24. So take that number, raise it to 24, and then whatever you get, write it down with all the decimals. $1.061757,044. Are you all still okay with what we're doing? No questions on any of the steps? And then, at this point, times, multiply these, right? And you have, let's see, 12741,084.53. That's what I'm getting. Anyone else getting that?
Yeah.
Yeah? So let me write that down over here. You have 12,741,084.53. That's where you are now. Everyone get that number? Did I do that right? That seems like craziness, doesn't it? How much money did you just make? $741,000. Right? You started with 12 million. Now you have $12,741,000 just for leaving it in the bank. Now, remember I asked you to think about a number that would make you happy? If I told you you could make $741,000 in 2 years, would you be happy? For the rest of your life?
That's if you don't touch that 12 now.
Yeah, but you're making money off your money. You see? Just leave the 12 million there, right? And then you do this again, right? You do it again, you leave the 12 million there, in 2 years you'll have 741,000. In other words, if you have a pile of money, you can just sit on that pile of money and live off of that pile of money. If you're disciplined enough to actually sit on it, right? That's why it blows my mind, these athletes that, sign these contracts for $150 million a year. I mean, $150 million for like 10 years. And that's like, okay, $15 million a year. Well, crap, we could make out pretty darn good if we had, 12 million. They're, 150 million, like. And then you have these people who are like billionaires, right? So look, if you move this, if you move these zeros over, okay? So let's say I added one more zero to this. And let's not even think about lottery anymore. Let's just think about somebody on the planet right now that's worth $120 million. All we need to do to figure out how much they would make over 2 years, I'm going to get rid of that decimal. Do you think they care about these cents? No. Is move one more zero in here. That's actually the way it would work.
Damn.
So if you had a, wait a minute, did I move that? I didn't move that right, did I? Yes, I did. I did. So if you had $120 million and you could invest it in a way that you could get a return of 3%, then in 2 years you would have $127 million. So you'd make $7 million in 2 years. That's roughly $3 million a year. That's just sitting on it. It's not even spending it. Right? The worst thing you could do if you hit the lottery is go blow half your money. If you're willing to wait a little bit, then you can just start living off of it. Because once it's gone, you'll never gain interest off it again. That's it. It's gone. So this is kind of depressing, isn't it? To think about, if you've got a lot of money, that you really don't even have to do anything. You're going to get paid for having that money. That's why there's these families and these, this historical, like these nest eggs that just get handed down from generation to generation, because they can just keep sitting on the money. Yes?